and thank you for attending this webinar. Today we're going to talk about measurement uncertainty. My name is Marc MacDonald. I've been working with NEL for the last 7 years now. In that time I've done lots of testing and research and calibration in NEL's flow facilities with various different types of flow meter, including single phase and multi-phase meters, as well as other different types of equipment. I've also worked on the design and upgrade of NEL test facilities and done consultancy work as well, including in uncertainty analysis. So measurement uncertainty is an area that's very important to NEL. First of all, because we host the national standards in the UK for flow measurements and also for density. And those standards have to be defined to a very, very low measurement uncertainty. And we have to provide evidence that those uncertainties are achieved. So because of this, we've developed quite a lot of competence in this area. And we're able to offer it as a consultancy service and as a training course as well. So let's get started. So we're going to cover various different topics in this presentation. So first of all, some basic uncertainty theory. We're going to look at the costs and implications of measurement errors. There's different types of uncertainties that are dealt with, so we'll cover those. Next, we'll look at the stages that are involved in a full uncertainty analysis for a measuring system. And finally, towards the end, we're going to look at ways that you can improve a measurement system using the uncertainty analysis and the uncertainty budgeting techniques. So first of all, why are we talking about uncertainty in the first place? Like, why are we interested in it? So this takes us back to the purpose of measurement in the first place. So when you take a measurement, what you're actually doing is estimating the value, the true value of a measured parameter using a measurement instrument. So there's various different types of measurement instrument. It could be something simple like a level gauge or a thermometer, for example, or it could be something complicated like a mass spectrometer or a flow meter with various different inputs. But the principle is the same in both cases. When you measure a parameter, you're actually making a sophisticated estimate of its true value. The true value is, strictly speaking, unknown. You can't know what the true value is, and you can only make good estimates. So we'll talk a bit more about this as the presentation progresses. But it takes us to the definition of uncertainty. So what uncertainty refers to is you take an estimate of the true value, you make a measurement using your measuring device, and the uncertainty is an interval that is applied on each side of the measured parameter. So the indicated value from the measuring device, you have an uncertainty above and below this value. And we expect the true value of the measured parameter to lie within this range somewhere. So if the uncertainty interval is well defined and well specified, then the true value will be within it. Now, there's also a confidence level attached to this as well. So depending on the uncertainty level, we'll have different confidence levels. So what the confidence level refers to is the likelihood that the true value lies within your uncertainty margin or your uncertainty interval. So one way we can improve the confidence level is by making the uncertainty larger, but obviously that's a less precise measurement, you could say. So the larger the value of the larger the size of the uncertainty interval, the greater the confidence you have that the true value lies within it. When you have a measurement, it's important to express three different aspects of the measurement. So first of all, we have the measured value, but we also have to express the uncertainty interval and the confidence we have in the uncertainty interval. So in this case, our example is a flow measurement. We've measured 3.5 litres per second, and in this case, the uncertainty interval is plus or minus 0.2 litres per second. And the confidence level that we have for this uncertainty level is 95% confidence. So what we're saying is that 95% of the time, we expect the true value of the measured parameter to lie within this uncertainty window. So we expect the true value of the parameter to lie between 3.3 and 3.7 litres per second. So we'll talk about where this number of 95% comes from later on in the presentation, but this is a very common confidence level. So in metrology, it's probably the most common confidence level that is used. So to give a visual representation of the example we just spoke about, we have our measured value at 3.5 litres per second, And we can see the shaded area covers the uncertainty interval. And we know that this uncertainty interval has a confidence level of 95%. So 95% of the time we expect the true value to lie within this range. And in this case, the blue dots represent the true value. So in this example, the true value is within the uncertainty limit. We also have to define, as well as uncertainty, we have to define what error means. So error is simply the difference between the measured value and the true value. So because the true value isn't known precisely or exactly, then that is also true of the error as well. So you can never know the true value or the error exactly. All you can do is make a very good estimate. So you do this by using high quality instrumentation and by following the correct procedures. And in that case, you'll be able to make an estimate that is fit for purpose. We also have to talk about standards and expanded uncertainties. So the standard uncertainty is the most basic form of the uncertainty. And we have two different values here. So the standard uncertainty corresponds to a 68% confidence level. And this is derived from statistical analysis. Later in the presentation, we'll show where these numbers come from. But all you have to know is that the most basic form of the uncertainty, the standard uncertainty, has quite a low confidence level. So only 68% of the time we expect the true value to lie within this uncertainty limit. So it might be desirable, in many cases it is, to increase the confidence level, and we do this by increasing the window of uncertainty or the interval of uncertainty. So when we have a higher confidence level than the standard uncertainty, this is referred to as the expanded uncertainty. So commonly you see the value of 95% for the expanded uncertainty. Now again, we'll cover where this comes from later on in the presentation. So to convert between a standard uncertainty and an expanded uncertainty, we need a coverage factor, which is defined here as the letter K. If you want to move between the standard uncertainty of 68% to the expanded uncertainty of 95%, you use a coverage factor of 1.96, which is sometimes rounded up to 2. We can see what the effect here has been. So we started with quite a small uncertainty, but a low confidence level. And now we've moved to a higher confidence level, but our uncertainty band has effectively doubled. So we have a less precise measurement, but we have greater confidence in the uncertainty. We also have to define what accuracy means. This is a very common term, and it's not always used in a technically correct way. So the accuracy refers to the closeness of agreement between the measured value and the true value of the measured parameter. It's possible to have an accurate measurement despite the fact that you're operating with a high measurement uncertainty. The difficulty with accuracy is it's a very useful term to use, but it's a qualitative term. You're not supposed to attach numerical values to accuracy, so it's not technically correct to say this device is 5% accurate. What you can say is that the device performs to a 5% uncertainty, for example. It's fine to say that this device is more accurate or less accurate than a different device, but the important thing here is not to attach a numerical value to a qualitative term. Repeatability. This refers to the closeness of agreement between successive measurements of the same measured parameter under the same conditions at approximately the same time. So the example that easily illustrates this is if you have a balance and you use it to weigh to measure the weight of an object repeatedly, you'll find that you get a spread of results, and hopefully they're in very close agreement. Another example might be taking resistance measurements of different types of resistor, or the same resistor. Or additionally, you can take repeatability measurements of a flow meter as well, so you can establish the same flow conditions repeatedly and see how consistently the device performs. There's actually several different ways of defining repeatability or different calculations that can be used. So it's important to state which method has been applied and what calculations have been applied in that case. In terms of the relationship between accuracy and repeatability, well, if you have good accuracy, then you also have good repeatability. This is because if you have successive measurements that are very close to the true value, then those measurements must also be close together as well. So there is consistent readings from the measuring device. If you have poor repeatability, then it is not possible to have good accuracy. Again, this is because you have a scatter of results, so if every measurement is different from the last, then they can't all be close to the true value. On the other hand, it's possible to have good repeatability but poor accuracy. So this is what happens when you have a very consistent performance from the measuring device, but it isn't accurate. So there could be an offset or a systematic bias that is affecting the reading of the device. This can sometimes still be useful though, because with repeatable measurements, you can at least determine if the system is changing or not. So there is some value in repeatability even if you don't have accuracy. So we've covered some of the basic concepts in measurement uncertainty. We just want to give an example of how this can actually have an effect on a process, or it can have real-world implications. So if you look at the amount of oil production from 2018, the worldwide figures of oil production, there was 99 million barrels of oil produced on average each day, and the total value of this oil was $7.92 billion. We can think about what the uncertainty in this measurement is. So if we assume that the correct practices were followed and the standards for custody transfer of oil were adhered to, then there should be a measurement uncertainty of about 0.25% on this figure. This equates to a financial exposure of $19.8 million per day. So we can see there's real financial incentives for improving the measurement uncertainty where possible. This figure of 0.25% is seen as being a good compromise between the cost of the measurement instrumentation and processes and the financial exposure that results from those processes and instrumentation. But it gives you a sense for how measurement uncertainty is important in the real world as well. And it's not purely an academic exercise. So to give a different example, we can also think about the cost of refueling our cars. So if we say that at the petrol pumps in the UK, let's say the uncertainty in measurement is 2% at 95% confidence. If you want to refuel a car that has a 50-litre capacity, what is the uncertainty in the filling procedure? So the total volume transferred is 50 litres, and at 2% we have an uncertainty of plus or minus 1 litre for every fill at 95% confidence. If every litre of fuel costs £1.20, then we can look at what the implications are for the uncertainty. So the overall cost of the filling procedure is £60, but there is an uncertainty in this case of plus or minus £1.20. If we assume this vehicle is filled every single week, then the financial exposure for the year is £62.40. So it's not a huge amount of money, but we can see there's still savings to be made here. So for this reason, petrol pumps in the UK, they do not tolerate an uncertainty of 2% like we've used in this example. The uncertainties we expect from refueling in the UK, the dispensers are allowed to under-deliver by 0.5%, but they're allowed to over-deliver by 1%. So there is a bias that favours the consumer. We also need to look at the different types of uncertainty analysis. So this information is presented in more detail in what's known as the GUM. I'll give a reference for that at the end of the presentation. But it's the guide to expression of uncertainty and measurement. So there will be a reference for this at the end of the presentation. But generally speaking, it's broken down into two types of analysis. So there's type A uncertainties and type B uncertainties. So type A uncertainties are based on statistical analysis of large data sets. So it's the most mathematically robust type of uncertainty analysis, whereas type B comes from less statistically interesting techniques. So type B analysis might be from a calibration certificate, for example. So there has been uncertainty analysis applied, but you're just taking a single value as your answer. Or it may be from manufacturer specification sheets. It may be from past experience and the advice of a consultant, for example. So the point here is that you don't have a large data set to perform a calculation with. You have maybe a single value or a small range of values. So the examples we're going to give today are mostly going to be type A numerical uncertainties, but type B are important as well. So with type A uncertainty analysis, there's a couple of different steps that are involved. So first of all, we have to find our best estimate of the true value of the measured parameter. And what we can see here is that we have a range of values that have been collected by the measuring device. And we can see that the red dot in this case represents the true value. So depending on the distribution, you would expect the best estimate of the true value to correspond to close to the mean value of your collected results. So it's important to work out what the arithmetic mean is, because that becomes your best estimate for what the true value is, based on the performance of the measuring device. We're also interested in the standard deviation. So I'm not going to show the calculation for the standard deviation. It's fairly commonly understood. But the point we want to get across here is that when you do a standard deviation of a large data set, that is equivalent to the standard uncertainty for that data set as well. So our basic definition of the standard uncertainty is synonymous with the standard deviation, and that's how it's calculated for type A uncertainty. When we start thinking about the statistical origins of these terms, then we have to think about the different types of distribution there can be for data sets. So by far the most common that we come across is the normal distribution, or the Gaussian distribution, and this is also referred to as a kind of bell-shaped distribution. What we have on the x-axis is the range of potential measured values, or just the range of entries in the data set. The y-axis represents what the frequency is of those measured values, or those data points. So we can see that with the normal distribution, we get a cluster at the mean. So by far the most common results occur close to the mean. And as you move away from the mean, you get less and less results. And this is a very well established distribution that's seen in many different examples. So if you take a large population, for example, of people, and you log the average heights, or the height of every person in that population, then you'll tend to find this kind of shape occurring. So there's a cluster at the mean, and then there's less and less people at the extremes. So the numbers of 68% and 95% that we've seen before, the confidence levels for the standard and the expanded uncertainty, well, this is where it comes from. It's based on the normal distribution, and they correspond to one standard deviation or two standard deviations. So what this means is that if you take a standard deviation away from the mean, plus or minus, you expect 68% of your results from this data set to lie within this window. So this is why you have 68% confidence, because it's based on an established distribution of data sets. If you want to work with an expanded uncertainty, then you can increase the confidence, but also increase the uncertainty level by applying a coverage factor. So we move from 68% confidence to 95% confidence using the coverage factor of 1.96, or approximated as 2. And we can see this corresponds to approximately 2 standard deviations about the mean. So this is where these figures come from. So the normal distribution is quite widely used, and it represents many different types of data sets that you're likely to see in mathematics, but also in nature. Another type of common distribution is the rectangular distribution. So what this means is we have a range of possible results from our measuring system. So we have a maximum and minimum, and we have a mean. But what you see with the rectangular distribution is that any of the possible values has equal probability. So you're just as likely to get a value at the mean as you are to get a value at the maximum of the range or the minimum of the range. So this is referred to as rectangular distribution because of the flattened probability distribution. So in this case, we have uncertainty based on this distribution. So this is different from the standard uncertainty for a Gaussian or normal distribution. In this case, every value is just as likely as the next. So the A represents the limits of the range. So the minimum value is minus A, and the maximum value is positive A. And the coverage factor in this case is square root of 3. So we'll see that in later examples. Rather than using a coverage factor of 2 for an expanded uncertainty of 95%, we use a coverage factor of root 3 for the rectangular distribution. So what does this actually refer to? Well, the rectangular distribution would be things like resolution uncertainty, which we'll look at in more detail later on. But what it means is maybe you have an instrument that doesn't read to a very tight specification, and you're having to guess what the true value is because you don't have sufficient resolution. The resolution uncertainty would be a type of rectangular uncertainty. So to give an example of this, we have a flow meter, and this flow meter isn't very precise. It only reads to the nearest whole unit. So this might be 35 litres per second, for example, or kilograms per hour, or any type of flow unit. But the point is, we can see the resolution is extremely limited. With this type of resolution, we cannot differentiate between values of 34.5 and 35.5. In each case, the reading will just be 35. So we have a very large window of resolution uncertainty as a result of the reading and the display of this device. If we want to increase the resolution uncertainty, then we need to read to a greater number of decimal places. So if we take the same meter and replace it with one that is more precise and reads to 1 decimal point, then we can see that the uncertainty window, or the uncertainty interval, the green block on the graph below, it shrinks considerably. So now we have a much tighter resolution uncertainty, and the contribution of the device display to the overall uncertainty is much reduced. So this is much more appropriate for a high accuracy system. We can also have bias in a measurement. So I mentioned this previously when we looked at repeatability versus accuracy. So what this means is you could have a device that has a fairly standard performance when it takes repeated measurements. Like maybe it measures roughly in terms of a normal distribution. So you have this spread of results where there is a cluster at the mean. However, if the device has been calibrated incorrectly and a bias was introduced at the calibration stage, then it doesn't matter what the distribution is. Your measured value, your average of the measured value is still offset from the true value of the measured parameter. So in this case, we have a systematic error that is introduced with every single measurement, in this case because of calibration of the device which is not performed correctly. So we still have a spread of results, it's just that they're nowhere near the true value of the measured parameter. And systematic bias occurs in many different cases, so it could be the calibration was carried out incorrectly, or it could be that the meter hasn't been zeroed correctly. That's a very common occurrence. Another obvious example of bias is if you have a watch and you set the time and the reference that you use to set the time on your watch is incorrect. So let's say it's out by a minute, and your watch is then reading 1 minute fast for the rest of the day, or the rest of the week, or until you calibrate it again. So whatever changes happen to the watch itself, there's always going to be that offset additional to those effects. So you have a systematic error that can't be removed without recalibrating. The distributions we covered so far were the normal distribution and the rectangular distribution. In statistics, there's also something that's referred to as a skewed distribution. And what happens with a skewed distribution is you get a separation between the mode, the most common value, and the mean, or the arithmetic mean. So we can see that the average, or the mean value, is separated from the mode. And an example of this would be something like the salary distribution in a company. So you'll see that most of the values are at the low to medium range, but you have some representation at the very high range, but only very limited frequency. So whenever you have a separation between the mode and the mean, this is referred to as a skewed distribution. So now I want to cover the different stages of an uncertainty analysis, and this is to cover the full uncertainty budget method that NEL tends to follow for our own internal facilities, but also for consultancy services. So the very first stage is to identify what the uncertainty sources are. So this can be quite a difficult process because there are many uncertainty sources that you know about already, and you might be able to quantify them very easily. But there's also uncertainty sources that you know about, but you don't necessarily know how to quantify. And the worrying thing is there's also uncertainty sources that you don't even know about, and you don't know that you don't know them. So inevitably there will be things that are missed out, but you just have to be pessimistic and open-minded and try to consider as many uncertainty sources as possible to get a complete picture. The next step, once you have your various different types of uncertainty sources is to estimate the magnitude of them, and the difficulty of this process depends greatly on the information you have available and the type of the uncertainty source. So generally speaking, a resolution uncertainty is very easy to quantify, and you can do it to very accurately without too much difficulty. There's other uncertainty sources that aren't so easy to quantify, so you could have something like the effect of electromagnetic noise, for example. This is something you'll just have to make a good estimate for and try to be conservative. When in doubt, you basically try to assume the largest value possible that is realistic. You try to be pessimistic rather than optimistic in this case. The key is to be conservative. So once you have your uncertainty sources and you have reasonable estimates for the magnitude of those uncertainty sources, the next step is to convert to standard values. So this would be converting to standard uncertainties. So you'd be converting from expanded uncertainties using your coverage factor to the standard uncertainties at 68% confidence level. And the reason you do this is that if you want to combine the uncertainty sources, they have to all have the same coverage factor. You can't combine uncertainties that have 95% confidence with uncertainties that have 68% confidence. So the most standard way of doing things is to reduce them all to standard uncertainties. The next step is to calculate the sensitivity of each uncertainty source, and you determine something known as a sensitivity coefficient. And we'll see numerical examples of this later on in the presentation. But generally this means if we have, for example, a system that measures the flow rate of a fluid, by measuring a collected mass and measuring the time it takes to collect it, then we have component uncertainties or input uncertainties of mass and time. But we want to know what the effect is on the overall flow rate uncertainty. So we want to know what the effect is on the measurement in kilograms per second. So we need to calculate what influence that has. So for a deviation in mass, what effect does that have in flow rate? And for a deviation in time, what effect does that have in flow rate? And this is how you get your sensitivity coefficients. Once you have the sensitivity coefficients and your standard uncertainties, you multiply these together to get your overall output values for the uncertainty source. Stage 6, we have to estimate the degree of correlation. We're not going to address this just now because this makes things a bit more complicated. So for the time being, we're going to assume that our uncertainty sources are not correlated, but this will be addressed at the end of the presentation. So if the uncertainty sources are not correlated, then the combination of uncertainty is a bit simpler, and we continue with the standard method. So you combine the uncertainty sources using a method that depends on if the sources are correlated or uncorrelated. If they aren't correlated, what we tend to use is the root sum squared method. So you take each uncertainty contribution, you square them, you add them all together, then you find the square root of the overall sum of those values. Once you have that, you have the combined standard uncertainty. You use a coverage factor to convert back to an expanded uncertainty, and that completes the process. So after following all of those steps, you now have a complete uncertainty analysis, but in actuality you don't. What you tend to see is that these uncertainty budgets or uncertainty analysis exercises, they're very iterative, and you have to go around the process several times to get it to become realistic and to find the most robust analysis. So it's very rare to complete an uncertainty analysis in one go. It's something that has to be continuously refined as you get more and more information. So that covers the basic process. We're going to look at it in more detail with numerical examples to give you a sense for what this actually means and how the process is carried out. But those are just the stages involved. So the example we want to look at, first of all, is using an orifice plate. So the orifice plate is used for flow measurement, and we have a governing equation at the bottom right-hand side of the screen. So we know that flow rate depends on the discharge coefficient, the beta ratio, the expansibility coefficient, the diameters of the pipe and the orifice plate, which gives you the beta ratio, as well as the differential pressure and the density determination. So there's various different components in the calculation, and straight away you can imagine how each of those has its own source of uncertainty. So each of those parameters represents an input into the overall flow measurement uncertainty. So we can put some numerical values down. So we have a very standard discharge coefficient in this case of 0.6. The expansibility factor is close to 1, but not exactly 1, so it's 0.997. So we're likely dealing with a gas here. The pipe diameter is 0.5 metres and the orifice diameter is 0.3 metres, with a pressure drop of 50,000 pascals and a density of 48.7 kilograms per metres cubed. In this case, a calculated flow rate is 100 kilograms per second. So we have the measured values for each of these parameters and the overall flow rate, but what happens when we introduce the uncertainty? So in this case, we'll take all of these inputs as uncertainty sources, discharge coefficient, pipe diameter, and all the rest, and we'll put them into a table. So we have the measured value for each of these parameters, but we also have an uncertainty attached for each, and these are all determined using different methods depending on what the parameter is. But for something like discharge coefficient, well, we can get that from the ISO standard for differential pressure devices. Assuming that the orifice plate is manufactured to the correct tolerances and it corresponds or it conforms to the standards, in this case ISO 5167, then we can get an estimate of the uncertainty for the discharge coefficient from that standard. So we're fairly confident that we have an accurate value of the uncertainty of the discharge coefficient. So in this table, all of the values that are in green are the uncertainty sources that we're very confident in, which have been determined in this case from a standard. So this is the same for expansibility factor. Pipe diameter and orifice diameter are based on the manufacturing tolerances of the device, which again should be in conformance with the standard. So we're very confident in those. For the pressure drop and the density, well, there's a bit more work involved because there's various parameters that feed into each of those. So with the pressure drop, for example, we have the performance of the pressure transmitters, but also the calibration which they were subject to, and the uncertainty of the standard which they were calibrated against. But then we also have the performance of the device under real conditions, like how repeatable is it, and what is the standard deviation and the standard uncertainty. With the density, well, if this is a gas like nitrogen, for example, we can actually work out the density using an appropriate equation of state. That equation of state would have uncertainties attached to it as well. And you would also need temperature and pressure, each of which would have their own component uncertainties. So you could do a deeper uncertainty analysis looking at each of the subcomponents of this table, but this is just a simplified overview. So if we want to combine these uncertainty sources, I mean, we're at stage 2 right now, but we can follow the process that we described previously. So if we want to go to stage 3, to do that we have to move between an expanded uncertainty to a standard uncertainty. And you can see the coverage factor under the column labelled K. So for most of these parameters, the coverage factor is 2. What we're saying is that the expanded uncertainty for each of these parameters is, the expanded uncertainty corresponds to a confidence level of 95%. So for each of the values where K equals 2, confidence level is 95%. We have 2 entries where the confidence level is actually different. So we have coverage factors of 1.73, which is a square root of 3. So these are resolution uncertainties. You can see that the manufacturing tolerance in terms of pipe diameter and orifice diameter, those are based on manufacturing tolerances, so they are resolution uncertainties. So for this reason, we have different K values for those 2 inputs to the uncertainty table. But once we have those, we can move between the green cells in stage 2 and the yellow cells in stage 3. So we divide by the coverage factor to get down to a standard uncertainty. We then have to consider the sensitivity coefficient. So this is how the input uncertainty influences the overall mass, or the overall calculated flow rate. So these are determined mathematically, and you can do it as a differential calculation, or you can do it as a trial and error calculation, basically. Once you have the sensitivity coefficient and the standard uncertainty, we combine those to get the overall component uncertainty. So in the purple column, we have the combined sensitivity coefficient and standard uncertainty for each of the input uncertainties. Now, we want to combine each of those, and they are uncorrelated, so what we do is perform the root sum squared method. So the very last column in the table, we're taking the previous value under the purple column, and we're squaring it. We then, from the top of the table to the bottom, to stage 7, we add all these values together to get a sum value of the squared values, and then we work backwards from right to left. So we can work backwards to find our standard uncertainty of 0.266, and if we want to convert to a 95% confidence level, again, we have to multiply by the coverage factor. So moving from right to left, we move from a standard uncertainty of 0.266 to an expanded uncertainty of 0.532. So this gives a numerical example of how this process is followed, and this is really the process that we use for our own flow facilities to develop that evidence. We're going to look at a slightly simpler example in this case, and now we want to look at how we use the uncertainty analysis to improve the accuracy of the measuring system. So in this case, we have a cylindrical tank, a storage tank, and we want to know what the volume of the tank is. So we know that the equation for the volume of a tank or a cylinder is fairly simple. We need the diameter, the height, and multiply those both by pi, square the diameter, divide by 4, and we can get the volume. So it should be a very simple process. But actually, there's some other things to consider. So local conditions like temperature will have an effect, and we have to consider the expansibility of the material. So there is a correction to be applied. If we take a standard temperature of 15 degrees Celsius, we might find that we measure under different conditions. So maybe we've measured the tanks at 30 degrees Celsius or 0. So we have to convert. But once that is done, we have a corrected volume measurement. So the calculation becomes slightly more complicated. If we decide to form an uncertainty table, then here's some of the uncertainty sources that you could consider. So you have the diameter measurement, you have the height measurement, then you have the effective temperature and the thermal expansion of the fluid and the effect that has on volume. For each of the diameter and the height measurements, there's multiple components though. So you have the calibration of those devices, you have the application of those devices, so the determination of the diameter and the resolution of the height measurement, and there's also a drift value as well. So over time the device will change and its performance will shift away from the calibration conditions. So each of these conditions has been considered, and we have our overall result. So if you look at the very bottom of the table, next to the entry for volume, we have an overall expanded uncertainty in volume of 3.188%. So this is good. We have a measured value and we have an uncertainty. But what happens when a regulator says to you, well, actually 3% uncertainty is too high, we have to get it below 2%. Well, there's then a process to be followed, like what is the best way to reduce this uncertainty? Chances are you have to spend some money on equipment or new procedures, but we want to find the best, most efficient way of doing that. So we want to find the most cost-effective way to target this system. So one thing you might do is look at the largest uncertainty contributions and improve those first. If you look at the right-hand side of the table, the overall combined uncertainty and sensitivity coefficients, this tells us which are the largest uncertainty sources. So in this case, the largest source is the calibration of the diameter measuring device. So if we improve that calibration, so either calibrate to a lower uncertainty standard or replace the device itself, we can bring that uncertainty down. So we reduce the calibration uncertainty of the diameter measuring device. So we've reduced it by half. The overall effect on the volumetric uncertainty is to reduce the uncertainty from 3.188% to 2.72%. So we're moving in the right direction, but there's still more work to be done. We can now see that the largest contribution to the uncertainty is not in the diameter measurement, it's in the height measurement. And again, it's in the calibration of that device. So either replace the device or improve the calibration by calibrating to a more accurate standard. If we spend some more money, we can reduce the uncertainties again. So in this case, the calibration uncertainty of the height measuring device is halved as well. So we've now moved to an uncertainty in volume of 2.22%. So we're getting very close, and we can now see that the biggest contribution to the uncertainty in the process is the determination of the diameter. So the diameter of the tank, the performance of that measurement is the biggest contribution that we have. So what we've seen with this process is that the diameter measurement has been performed using straps. So you're measuring the outside diameter of the tank and determining the diameter that way. So if we say to the measurement engineer, well, instead of taking 5 measurements of the tank, we want you to take 100 measurements, and then we'll get a more robust statistical analysis. If we do that, again, we can reduce the uncertainties of this component. So finally, by reducing the diameter determination uncertainty, we've got below 2% on the volumetric, the volume determination uncertainty. So we're now at 1.66%, and our job is done. So this is just a hypothetical example, but it gives you an idea of how the process works and how the uncertainty table or budget actually has real-world applications. If you're trying to improve the measurement system, then this gives you the information you need to spend the money in the appropriate places where it gets the best possible use. So one thing we didn't explain previously was correlation, and we're just going to quickly consider this. So far we've looked at uncorrelated uncertainty sources. In this case, we're going to look at correlation between different measuring devices for flow rate. So in this system, we have two different flow meters, and we have a combined flow rate, which is based on the measurement of both those devices. So we have a flow meter at location 1 and a flow meter at location 2. Each of those has a measured value, a true value, an uncertainty, an error, all these different components. If these devices and their uncertainties are uncorrelated, then it's fine to combine the measurements of them using the root sum squared method. So the calculation for that is shown in the bottom right-hand side. The overall uncertainty for the combined flow rate determination is based on the uncertainty of flow meter 1 squared plus the uncertainty of flow meter 2 squared, and find the square root of that. This is fine because we expect the uncertainties and the errors of each of these devices to be uncorrelated and somewhat random. So they combine in an acceptable way. However, if you find that the meters actually have a systematic error applied to them, so maybe they've both been calibrated at the same source and a systematic error has been introduced, then you then have correlated uncertainties, and it wouldn't be appropriate to combine them using the root sum squared method. So for correlated uncertainties, the method of combination is just a simple addition. So rather than squaring each of the values and then adding them together and then finding the square root, you just add them together. And the reason for this is that both of these devices in this case have the same bias. They both have a negative error and a tendency for those uncertainties to propagate. So this is how they are resolved. There's more information for why this works in the references we're going to mention, including the GUM, the Guide to Expression of Uncertainty and Measurement. But this is a general principle. So there's a couple of steps that have to be followed. As I mentioned before, working to standard uncertainty greatly simplifies things because you don't have different expanded uncertainties with different confidence levels. You can always combine uncertainties if they have the same confidence level, but the preferred way of doing this is to convert to standard, so the 68% confidence level. You want to make sure that all the units you're working with are consistent, so you can't mix litres and metres cubed, for example. That's just a general principle for calculations using any unit system. Generally, you want to work to two significant figures for uncertainty. Additional significant figures doesn't tend to add much benefit. And you always want to round up as well, so when in doubt, be conservative, be pessimistic. This is a process that's well suited to glass half empty people. And the whole way through the process, you have to think, does this seem correct? So generally, when you do the first pass of the uncertainty budget, you'll probably find that your values are much too optimistic, and your overall uncertainty isn't achievable based on worked experience and what you know about the system. The reason for this is that you haven't considered enough uncertainty sources, or you haven't applied the correct value to each of them. But generally speaking, after further revisions, the uncertainties tend to increase rather than decrease. If you do want to decrease the uncertainty of the system, you can improve the choice of measurement devices, or you can collect additional information that allows you to refine your estimates. But generally speaking, it's a pessimistic and conservative process. So the reference I mentioned before is the GUM, or the Guide to Uncertainty and Measurement. This is a widely accepted standard document that is used by metrology institutes all across the world, and it was compiled by a consortium of many international bodies, including ISO and OIMO, the standardization organizations. So it's a very good reference to give more detail on the statistical basis for these techniques and how they are applied. Highly recommended as fuller reading. So to summarize, measurement is all well and good, but one thing that you do need to know is how good is the measurement, and the way you do that is by stating what the uncertainty is and what the confidence level is, and that gives real meaning and weight to your measurements. It allows people to realise how important they are for making a change in their process or improving operating conditions and having a greater understanding for financial reasons. And as we can see here, the analysis of uncertainties is quite a time-consuming process, and you have to be very careful. There's many unknowns that have to be discovered, and it's something that's very easy to get it wrong, so you have to be very careful. It's quite an involved process. However, with a complete uncertainty analysis, it gives you a lot of important information about your process and where to make improvements, and that's certainly been the case for our own experience with operating national flow standards and providing the evidence needed for those. So hopefully you found this informative and interesting. There's a couple of upcoming events that NEL have organised in the UK and internationally. So we have the Oil and Gas Focus Group, which is one of our regular events, based in Norwich in this case. It changes between Norwich and Aberdeen. We also have an event in Texas, advertising our new high-pressure multi-phase flow facility, and there is an uncertainty measurement, a measurement uncertainty training course in May, that's in Aberdeen. So you can see there's many different cases where the uncertainty and measurement is really important for each of these. The next webinar is in May as well, and this is based on produced water. So at this stage, if there's any questions, I'd be happy to answer those. If there's any we don't answer today, then I can follow up at a later date. But thank you for attending, and I look forward to seeing your questions and comments.
Okay, thank you for that, Mark. If you just bear with us just for a couple of moments, and we'll just see if there's any questions that have been submitted. So there's one there, maybe, Mark, that you might want to take.
Yeah, so there's a question, where is it we see the skewed distribution? The skewed distribution isn't something that we tend to come across in measurement uncertainty. Generally speaking, we tend to deal with normal distributions or rectangular. Those are the most common. There may be applications where they do exist in measurement uncertainty, although there's many applications where they exist in other areas. So they occur in nature and they occur in different statistical analysis types. So the example we gave before for a skewed distribution was the salary profile of a company. You can also look at things like the age of death in developed countries. It's quite a grim example, but it's an obvious one. Things like particle size distribution as well. So it's not so much about measurement uncertainty, but it is measurement within a scientific context. So there's many examples where it is relevant, but we don't tend to apply it that often. The point here is just to show that there isn't just two distributions, there's many different ones that can occur for large data sets.
Another one there, Mark?
So we have another question. So how do we know the true value is within the uncertainty? There's actually many different answers for that. So in the simplest example, you can think about the practicality of the measurement. So if you're in an environment and you measure the ambient temperature and it says it's 150 degrees, well, you know the measurement is wrong. If it says the temperature is 15 degrees and you're quite comfortable, then you know that within reason the device is accurate. So you know that the uncertainty is maybe less than 10 degrees. So you can start to get common sense agreement between these types of things. The other thing you can do is, if you have measuring devices, you can use multiple measuring devices of different operating principles, and if they generally agree with each other, then you can get a feel for what the uncertainty is. So in that case, the disagreement between those devices could be your uncertainty as a pessimistic first pass. On a more scientific sort of basis, our measurements of devices are calibrated against standards, and at the top of the chain you have primary standards. Now, primary standards for measurements are usually based on universal constants and hard scientific principles. So they have a rooting in something that's a bit more robust and something we can put our confidence in. So, for example, the standard for the unit of distance is the metre, and that's based on the performance of light and how far it travels in a space of time. So with those standards, there's cross-checks that you can make to show that actually the true value is highly likely to be within the uncertainty limit. And the other thing you can do is have agreements between primary standards as well, so you can do intercomparisons. So again, if you have primary standards which are based on different operating principles at different locations, but they make the same measurement and they agree, then you have a very high confidence that the true value is within those uncertainty levels. So it's largely about practicality. It's for example, if you're trying to measure distances and you can only measure to the nearest metre, then you can't build an airplane. It just doesn't work. So we know that through practice that in many cases these values are where we expect them to be, but there's also more sophisticated ways you can prove that. So it just depends on the application. For us, in our facilities, we have a lot of experimental data which cross-checks a lot of the assumptions we make, and we also test customer test devices which have been calibrated at different facilities under different conditions. So when we find agreement between our facilities and dozens of flow meters, then we know that we're doing something right, and it backs up our previously held assumptions. So there's many different answers to that question, but it's something you really get a feel for when you're actually applying these techniques. And the uncertainty analysis is a very useful way of documenting it and improving the system.
Okay, thanks for that, Mark. You got time just for one more question?
I think it's probably best to answer the rest by email, I would say.
Okay, thanks for that, Mark. Ladies and gentlemen, that concludes our event today. I think that's us approaching the hour. As I mentioned at the start of the presentation, we will be sending you a copy of both the presentation and the recording, and hopefully we'll get that across to you early next week. If you'd like more information in the meantime, Mark's put his email address up there. You've also got my email address as well if you need to get in touch with us. As Mark said, and as I mentioned earlier on, we've got a note of all the questions, and Mark's going to take some time out afterwards, and he'll get back to you individually with the answers to your questions. So on behalf of your presenter, Marc, I would like to thank you for your time and for joining in today's event. You may now disconnect, and once again, thanks and enjoy the rest of your day. Thank you.